Okay, so we've been talking about light as both waves and as photons, as particles due to Einstein. So the evidence of wave nature of light is primarily the fact that it causes diffraction and interference. For instance, if I have a green laser here, and if I shine it on a grid, let me try it on this grid here, and you can see right there the grid of pixels that the cell phone, this is just an ordinary cell phone by the way, so the grid of pixels that the cell phone screen is made of right there in that diffraction pattern that you see from visible light of green colored light, which has got a certain energy photons defined by E equals hc over lambda, right? This is what we talked about. Photon energy is hc over lambda. What Louis de Broglie said is that why should this apply only to photon? This could apply to electrons as well. If that's the case, if you know what the energy of the electrons is, then they should have a certain wavelength associated with the electrons as well, right? This is the photon wavelength. So let's see, if electron behaves like particles, it should also behave like waves, so it should undergo diffraction pattern. If you take kilovolt energy electrons, then the wavelength of the light that you get is very, very small. So that light is so small that the pixel pattern that we have on the cell phone screen is not sufficient, but that's about the size of the spacing of lattice sites in a crystal. So here we have a device which is basically a electron tube, just like the cathode ray tube that we used before. So the electrons are coming in. I'll show you the tube in a little while. But they put a crystal in the path of the electrons, and because of that crystal in the path of the electrons, you see a pattern just like what we saw the pattern here. The spacing of the electron dots that you see on the zinc sulfide screen, which is placed here, is such that you can actually measure the structure of the crystals at a very, very fine spacing, that there is interstitial spacing between the crystal atoms, if you like. And you can do spectroscopy with this with a very careful way, using the electron diffraction. Let me turn this around so you can actually see the electron tube. This is not light, this is actually electrons coming in and striking the zinc sulfide tube here. So there's the vacuum tube, and there's the cathode over there. The electrons are coming from there, and somewhere in the midst of that there is a crystal. There's the cutout that you can see from here, the physical device, but there's a drawing in the slides that you will see which shows how the electron diffraction setup is. So both photons and electrons behave as waves and as particles. This wave-particle duality is the intrinsic reason for the world that we're in. Quantum mechanics and the uncertainty principle of Heisenberg, all of them follow from the same little thing, that both light and matter behave as both particles and waves. That's the end of class. There you go.